Okay, so for today's video, I'm going to be doing one that involves quantum mechanics stuff. And here we go. So the problem is, given a wave function, and you know these are all positive real constants, you want to normalize, find these expectation values, and then find the standard deviation. And the way we're going to do that is we're using these three things that are very key to doing problems like this. You know, since it's probability, if you integrate across the whole thing from infinity to infinity, it's going to equal 1. And that is the wave function times the wave function, that's the conjugate of the wave function, because it can take imaginary values, which there is an I there. And this only works if it's normalized. There's another thing you can use, but because it's normalized in this type of way, because that's what we're going to do using this. Any function acting on x, you take the expectation value of it, you plug it into one of these, and that gives you what it is. But for instance, this thing could be an operator, and you just put in what the operator is if it's momentum. The last one, you're gonna be able to use what you did for this thing to solve for this thing. So it's kind of like a hierarchical problem where you start up top and go down. Okay, let's hop right in. So how are we going to normalize? Well, I'm going to apply this. So the conjugate times the non-conjugate, the normal function, is going to get rid of this, but I'm going to write it out. So the conjugate times the normal, these are exponents, so things in the exponents add when they're multiplied together. So you're going to get an A times an A, and then this thing is going to become e to the 2 lambda absolute value of x, and then you're going to add the conjugate. So the conjugate is this whole same thing. You flip a negative to a positive on this I. So when you add them together, it's going to be a positive one of these on the top plus another one of those, so it becomes e to the 0, which is just 1. Or you can write it out. So it becomes e to the negative I omega t plus I omega t. So this thing just becomes a squared e to the negative 2 lambda absolute value of x. Okay, so this becomes this guy. Okay, so now we use what we did here and to here to get what it should be normalized with. And the way you normalize it, if I didn't state already, it's basically some factor times a will normalize it across over the whole domain. So when you do that, you set equal to 1 to find what a should be, because it's just a factor. So you get 1 is equal to a squared from negative infinity to infinity of e to the negative 2 lambda absolute value of x dx. Okay, a is a constant, so you can take it out in integral. But for this guy, you're like, oh, how do I integrate it? Well, you know, this function, in this case, right here, is even, and it's symmetric across the whole thing. So to get rid of one of these infinities, you can just change the bounds from 0 to infinity and multiply the whole thing by 2, which is how you're going to solve this guy. So 1 is equal to 2 times a squared from 0 to infinity times e to the negative 2 lambda. So when you did that, you don't have to worry about this absolute value sign anymore, because it's always going to take positive values for x, because that's where we changed our limits of integration to dx. And that becomes a simple little integral to do, but your bounds are still 0 and negative infinity. And to properly do that, you can set infinity to a parameter and take the limit of it as it goes to infinity. But you know, it doesn't really matter because in the end it's just going to be some number. So you get something like this. Integral of that you divide by whatever it is times x. So it's 2 lambda. And then it's multiplied by the same thing up top. And you do from there to 0 to infinity. And as you can see, I could have took the limit of like some parameter for this value here, but it's just going to be what? 1 over infinity is 0 minus e to the 0 is 1. So you get 0 times 1 times this. So it becomes a squared negative over lambda. So that negative sign goes away because that was negative 1. So the normalized factor you get is the square root of lambda. Okay. So we normalize our wave function, knowing that lambda, square root of lambda is equal to a. So now when we do this guy, we can apply it right away. We don't have to worry about some other form. Alright. I'm gonna erase forward real quick. Okay, so now we know what our normalized wave function is. We can apply this guy to find what the expectation value is for x and x squared. So the only function in this case is just x, and in this case the function is icon x is squared. So that's why when you do it for this case it's just x, and then when you do it for this case it's x squared. But what does it look like? So you take negative infinity to infinity for the first case, just for the x, and you use the normalized a when you plug it into here. That's the conjugate times the normal one, but these have to be the normalized wave function. So you get this. A lambda to the square root times another lambda to the square root is just lambda. And this guy goes away just like in the last case. So you're left with something like this. E to the negative 2 lambda absolute value of x. And I could have slapped the x in there, but I know multiplication is commutative, so you can switch it around. So it's this whole thing times x dx. Alright, so in this case, you're wondering how do you integrate this one, but you can do this one kind of like how I changed the bounds, but in this case, you don't have to worry about solving the integral because it ends up being an odd function, x, times e to the absolute value of x times something, which is an even function. And when you graph the odd multiplied by an even function, you get something like this. So this guy is always going to be positive. In this case, it's e to the some factor to the absolute value of x. So no matter what x is you put in for this guy, it's always going to give you some positive value. So the only thing that's going to change where this guy is going to be the odd function when multiplied. So when it's negative, it's going to be a negative result. And in this case, you're integrating from negative infinity to infinity. So what does that look like? You're going to be adding up all the areas in negative and all of these. So that ends up being that whole integram when you do from negative infinity to infinity. In the symmetric case, it's going to give you 0. So that's what you do for this guy. But for the other guy, you can't do that. In this case, you get an odd function times an even function, and it's symmetric in the bounds for the integral. But so now we know the expectation value for just the x function is 0. Alright. So now for this guy, you do the same thing. You start out the same way. This time it's x squared. And maybe I'll write it out a little bit more this time. So the conjugate, it's just over lambda e to the negative lambda absolute value of x. I could say what? Plus I omega t. And then I slap in my x squared, multiply lambda, e to the negative lambda, absolute value of x, minus I omega t. So in this case, I wrote it all out just for fun, just to show you if you didn't catch what I did before. So these are gonna go away because they're opposites. And then these become just lambda, and this becomes e to the 2 lambda, absolute value of x, and x squared, it's just x squared because there's no other factor on the bottom. So this one, in this case, you get negative infinity, lambda x squared e to the negative 2 absolute value of x dx. Okay, so we can do the same argument when we normalize it. It's just an even function, and its bounds are symmetric. So we can multiply the whole thing by 2 and change it from 0 to infinity. So what does this become? 0 to infinity. I can take out this constant lambda, x squared, and multiply the whole thing by 2. That was the whole point. E to the negative 2 lambda. I don't need this absolute value no more. Dx. Okay? So when you get to this part, you can do this. The same way how I said you could take the limit of this integral as this parameter up top goes to infinity, but you don't have to worry about that. But what we're going to have to do is we're going to have to apply integration by parts twice if you don't want to use an integral table, which I'm going to do, because I don't like memorizing tables. Okay, so I'm going to write this. I'm going to set this equal to k naught, so don't worry about it later. So how do you do this? Well, I'm going to choose u to be x squared, and dv is e to the negative 2 lambda x. du is equal to 2x. Oh, I should have wrote dx. Doesn't matter. It's just a little substitution trick. And what I get, v is equal to okay, you multiply these and minus the integral of these multiplied. So one substitution of integration by parts gives you get x squared, remember times this k naught, times e to the negative 2 lambda x over negative 2 lambda. And this whole thing on the limits of integration, you can plug it straight in. 0 to infinity, but if you quick glance, you plug in infinity, you get 0 times infinity, which is 0, and then you get 0 when you plug it in, you get 0 times 1, so it's 0. So this whole thing becomes, k naught times 0, which is 0. But you're left with these two guys on the integration by parts. So you're left with 2 times 1 over negative 2 lambda, and it's negative, so I plus it. And I get rid of the 2's, times k naught, and it's the integral from 0 to infinity of x times e to the negative 2 lambda x dx. So what you end up doing here is another one of these. So everything up to here is kind of pointless, so I'm going to clear up some room for the board real quick. And just remember, this whole guy is equal to this. So now I can erase everything else real quick. All you have to do was apply one more integration by parts. So I leave this constant out. So you take u to be that and dv to be that. So you say u is equal to x, dv is equal to e negative 2 lambda x, du is equal to 1, v is equal to that guy. Do it real quick, and you get the same thing with this term over here, right? Times k naught over was lambda. So this guy's gonna become 0 again in the same way. If you take the limits, you plug them in, you get 0 times something and then another 0 times something minus another negative number there. So it becomes positive. And this guy was positive right here, so I don't have to worry about my sign because I kept track of it. So you multiply 1 over 2 lambda, multiply by k naught over lambda, integral 0 to infinity. Multiply these guys, so it's just e to negative 2 lambda x dx. So what does this become? Do it real quick. Since it's basically the same one we did when we normalized, I can tell real quick it's going to be 0 minus 1. But I have to multiply by this integrating factor to get back in with the antiderivative. So it's 1 over negative 2 lambda as well. Times this guy over here too. So what does that become? It becomes a positive number. So, and also I have to recall what k naught was, and I believe I wrote it down, so I wasn't done. K naught ended up being 2 lambda. So I get 1 over 2 lambda times 2 lambda over lambda. Negative, negative, positive, so 1 over 2 lambda. So what does that become? These go away. All of these go away. And 1 over, so it becomes 1 over 2 lambda squared. That is equal to this expectation value function of x squared. Okay, so for the last part, we have to apply this guy, which is pretty easy because that's what that is in statistics. So, for the last question, it said find the standard deviation. It ends up being, we know what this guy was, it was just 0. But we know this guy was also, so I got 1 over 2 lambda squared minus 0 squared, right? Which is just 0. And to find the standard deviation, which is equal to the square root of all that. So what do you get? It's 1 over radical 2 times 1 over lambda. And just to recall, this guy was my x squared and this guy was my x. Just in case I erase it too quickly. Okay, so in this problem, you just have to apply these statistic stuff. And in this case, remember to normalize, because you can't use this type of expression for some expectation value if it's not normalized. You have to apply some other thing where you divide basically by the wave function. That isn't normalized yet. Okay, have a good one.